interactive demos in addition to all of the exhibits. Plus, we have a panel organized. They still keep awake for all of this stuff on the future directions of for translation of technology into clinical areas. So we've tried to put together, with your help, because really it's only the missions that drive a lot of what's going on here, to put together an interesting and informative program, in addition to having the awards, as Emily mentioned, organized by Jeff and this committee, to acknowledge best papers and best posters. Emily mentioned already most of the names of the people that have been so very dedicated to running the conference. These names have been mentioned, I think, already, so I won't go into it. But really, it's a very much of a shared effort, which would not be possible to be done in any kind of way without that. And what I would actually like to do now is take a moment. There you are, Greg. This may come as a surprise to you because, as far as I know, we did not leak the information. But what we would really like to do is to acknowledge your leadership, your dedication, and your service over the years. In fact, for those of you who are not aware of Greg, it's hard for me to imagine who's not aware of Greg, who is a professor of computer engineering and director of the Telerehabilitation Institute at Rutgers University. Greg has, in many key ways, pioneered the development of our field and the continuation of it. Greg graduated from New York University with a PhD in robotics. He's a recognized pioneer of virtual rehabilitation and a world expert on haptics. He's authored over 100 scientific publications, including the books Virtual Reality Technology, Force and Touch Feedback for Virtual Reality. He served as general chair for ICVR in 2000 and was very active in giving workshops at a very early stage. In fact, I don't want to either age Greg or myself, but I will mention that my very first opportunity to be exposed to the world of virtual rehabilitation was at a workshop that I attended in 1998 held in Atlanta. And Greg really helped me to understand the beauty and the challenge of the field. And I've always been grateful to that. And not only that, but when I went back to Israel after that workshop, I thought, well, I'm now a quasi-expert, and I certainly can give a talk on this, but I didn't have any raw materials, and those were in the days before you could just easily download a video clip from a website. And so I wrote an email to Greg, and I said, you have to show some really nice videos. I'd love to get a copy of them to show at this presentation. And he actually made copies of his video cassettes at the time, they weren't CDs even, and couriered them to me. And I just couldn't believe it, that I actually got from Greg Berdea material of that caliber that he so shared willingly. And I think that sense of sharing has been very much a part of Greg's modus operandi throughout the years, and we've all benefited from it. He's a fellow of the American Institute for Medical and Biological Engineering and senior member of IEEE, co-founder of the International Society of Virtual Rehabilitation, which you will be hearing a lot about throughout the conference. There will also be a general members meeting, which you're all invited to, and is the founder and president of Bright Cloud International Corporation, a rather small life. So Greg, please come to the podium. And in recognition of really your amazing contributions, and without a handshake or a kiss, I'm giving you this plaque.
They say that professors cannot keep secrets, but they did. This is a complete surprise to me. I'm honored for receiving this award. To my knowledge, it's the first for our conference series. As some of you may or may not know, I'm stepping down this year from being the general chair of the steering committee which oversees this series of conferences over the years, and I'm happy that we got to the 10th anniversary of this conference, which I started together with Professor Daniel Talman from Lausanne in Switzerland, who unfortunately couldn't make it here. And I'm very gratified as a scientist that I see this field growing. And I think you share with my belief that it's a very important field and that we have a very significant impact on the society, directly through the health of the subjects that we're treating, but also generally their family, the costs, the medical costs. And if you think that we've done all we need to do, of course we are wrong. In fact, the heavy lifting is coming. I don't know whether Europe shares a situation that we share in the United States. Definitely Japan does. Is anybody from Japan here? Sometimes we have people. Japan, just like the United States, has a severe aging problem. In the United States, the NIH report says that while Alzheimer's disease affects a few million Americans these days, and it costs $50 billion a year in medical costs, by 2050, the medical cost just for Alzheimer's will jump to $1.5 trillion. Okay? That's a budget of some countries, the total budget. Now, through virtual rehabilitation, a term that initially some clinicians didn't like because they didn't know whether actually the patient would think this is real therapy, but obviously we know it is. Through virtual rehabilitation, we can have a significant impact on the way therapy is done today and improve it, make it more efficacious, cheaper, at a distance, engaging. Hundreds more repetitions than conventional therapy can induce in a standard therapy session and so on and so forth. So as I said, I'm stepping down as the general chair. Tomorrow is taking over. I know the conference will be in very good hands. I urge all of you and you in turn to bring young blood into this scientific community. We need young people to take over, to bring their energy, their enthusiasm, their can-do attitude, because they were not told that something cannot be done, okay? It can be done, and to grow this field further. So I thank you, and I thank Emily Keshner for the great work to organize this conference. Thank you for your work.
Thanks very much, Greg. Just two more thank yous. Judy, would you just come up here, please? I really want to give a personal thank you to Judy, who has just really been amazing in doing the co-chairing, so thank you very much. Oh, you want to kiss?
Oh, okay. I just want to say, Tamar did all the work. She keeps thanking me, but she did all the work.
And Judy is going to make yet one more.
So, Emily, we want to recognize you because I don't know how anybody volunteers to organize a conference, but thank you for doing it.
I'd like to ask Dr. Sue Cobb from Nottingham University, President of the International Society for Virtual Rehabilitation, to come and introduce the first keynote speaker. I wish you all a wonderful and informative conference.
Thank you very much, and I'd just like to have my thanks to everybody for all the hard work and all the conference together, which I've heard. It was a huge effort. And I thank you all for coming along and joining into this community. So, to start things off, it's a very great pleasure to introduce Dr. Badler as our first keynote speaker. Dr. Badler is a professor of computer and information science at the University of Pennsylvania. Can we not hear me? Can you hear me? Did you hear any my very great pleasure to introduce Dr. Badler as our first keynote speaker. Dr. Badler is Professor of Computer and Information Science at the University of Pennsylvania. He's been on that faculty since 1974. He's been active in computer graphics since 1968 and has over 200 technical papers. Have a look at his website and see how much he's done. He'll be telling us about this himself. His research interests include embodied agent animation and simulation, human-computer interfaces, power modeling and control, computational connections between language and action. Among the centre's achievements are the human modeling software system, Jack. It's now marketed by Siemens and actually hugely influential in the community in which I work, which is human practice engineering. Jack modeling system is now standard in our undergraduate training programs. Dr. Badler's work embodies the most basic concept that we're trying to address in our field, that of identifying how the human agent reacts and transferring that knowledge to the virtual world. In his talk today, Dr. Badler will review his work on procedural motion generation and contextual motion of groups of virtual people. I very much look forward to his talk entitled Approaches to Human Motion Animation.
Thank you very much. It's a pleasure to be here. Thank you, Emily, very much for inviting me. It's always nice to know a few people. Greg Bergia and I have known each other by conferences for a long time. There are a few others of you. And I'm probably going to be anomalous with respect to what a lot of you are talking about, but a long time ago I heard a talk by someone who said, the more outrageous things I say, the more you'll listen. So perhaps that may be the way to treat this particular talk. I also slightly changed the title. I actually prefer the second one, is that I have this lifelong quest to control virtual people. I still didn't do it really well, but that's kind of a guiding light. So one of the important things certainly for young researchers, I don't want to be too pedantic here, but it's good to have a long vision. My vision may not be the same as your vision, but I was lucky early on to try to ask some questions that I had no idea how to answer. And some of those were, how do we actually get virtual representations of people to do things? And in particular, how to have them follow and execute instructions. And along the way, that meant I had to delve into a variety of very interesting issues that I wasn't trained in, but essentially became trained through collaboration with others. And because ultimately we live in communities and we interact with other people, the question of how do we actually make an interactive populace or an interactive community out of these people became the more recent question of the last decade. So giving someone like me a forum is always a dangerous, especially with an academic. When an academic has been around a long time, I appreciate the privilege to give you a little background because I want you to know where I'm not coming from, something else. So I did my PhD work at the University of Toronto, and I had 3 mentors there at that time who ended up being extremely influential in different ways. I sort of started as an artificial intelligence guy under John Mylopoulos. I was fortunate to be the first teaching assistant for the new graphics fellow, graphics professor Ron Becker. So he taught me computer interaction, and I actually learned computer graphics from an artist, Leslie Mezzi. So from these unlikely connections back in the early 70s, I started looking at a number of questions at that time related to computer vision, and I was interested in computer vision of humans, right? Back in 1974, when the thesis was about, can you make a computer look at people doing things and describe what they're doing? And by a few years later, I realized that was a hopelessly hard problem in a variety of respects, so I gave up on real images and started using synthetic ones. And in order to make synthetic ones of humans, I had to build synthetic humans. The rest is history, right? So we started doing this work when I moved to Penn in '74. It's hard to believe that was so long ago. And we started working on a wide variety of different problems to try to essentially build real-time interactive virtual humans. So there are many things that happened in that interim. Not all of these are PhD theses, some of them are. In the mid-90s, 20 years ago, it's really scary, we were working on medical simulations for DARPA, for example. Susan kindly mentioned the JAC work, which came out of the human factors community. But along the way, we realized that our approach was one that was sort of divisive. My joke, if I were giving this talk, which I'm going to repeat anyway, 10 years ago, is we divide the human body into graduate schemes. There were people who did arms, and people who did legs, and people who did eyes, and we certainly continue doing that. But in the last decade, we've tried much harder to put these things together. And if there is one thing that is difficult in the academic world, it is integrating pieces either that you put together before or that others have put together. It's very difficult to get graduate students convinced that integration of other people's work is any value. It's still difficult. So anyway, this is an interesting history, but I want to move on to give you a view of where we stand today, with a focus mostly on groups of people, right, as opposed to individual bodies. And some of that is because we don't do that much work of the JAC sort anymore. We don't really do much physiology, and we really don't do any virtual rehabilitation. So a lot of this is going to be in your imagination to connect together how it might apply and what we ought to be doing, especially if there are collaborations in the offing. All right, so my background was in this AI user interface and graphics amalgamation. So I bring concepts from all of those to bear. I'm not just I don't think I'm not just a one idea, one methodology kind of person. I see needs for all of these things. So, for example, from the artificial intelligence side, I find dealing with representation, dealing with semantics, dealing with what properties and affordances do objects and agents have to be very important. Looking from the computer graphics side, of course, we would like our animations to look as realistic as possible, but pure realism is not a goal. First of all, it gets in the way of things, and secondly, we're not in the business of making motion pictures that people are going to pay money to go see. We need to do just enough to get things that look realistic, and I've culled a lot of old animations out because now I look at them and we laugh at how bad they are, but at the time, 20 years ago, it was very difficult to make reasonable quality animation. So if I can give you sort of a holy grail of what we keep in mind as for what we're doing, I hope many of you have seen the Truman Show. And if not, that's your assignment tonight after you go through all the nice things that they're having you do here. But basically, the Truman Show's plot is an individual is taken at birth and raised in a virtual world. And all the other people in this world are actors, and they're all directed by a director who's basically scripting out this person's life. So what we like to have as an analogy is the subject, or the user, or maybe the patient is Jim Carrey, the poor guy in the middle, the poor guy who's being directed essentially, and everyone else is an actor. And what's interesting about that is that the actors know what they have to do. They don't have to really think too much, but they have to react to the principal character. So if we abstract this away from moviedom and look at things that people are willing to fund, for example, the U.S. Army, thank you for present support. The question is, how can we construct a virtual community that's convincing enough for someone to feel like they're actually inhabiting it? Okay, now, again, if you want to think about how this might apply to some of the things that you do. That discussion would be very interesting when I go through this. Okay, so what do we want to do? We want to produce individual, but preferably groups of people. We like to be able to use that elusive word easy to create them, modify them, give them some life. And one of the quests of the last couple decades has been I don't want to use the word language because that sounds like natural language, but a representation or an ontology, if that's your thing, a representation that lets us describe what the inhabitants, the people, the objects, and the environment want to do. So I'll talk a little bit about using the idea of events to control individuals as opposed to individuals making events happen, and end up perhaps closer to, but not giving you any real secrets about how to make events into immersive narratives. Right now, of course, what I think is guided by what my PhD students and postdocs think, and I have a student who really, really wants to build immersive real-time narratives. So some of the things that come out of this has turned out to be based on his belief that kind of organizing principle is what you need. You want to tell a story in order to engage. All right, so there's been a lot of work in crowd movements. I'm going to take some leisure here and not talk about these other people's work, though it is quite a community now. 10 years ago, there were literally a handful of papers on crowd simulation, a few techniques. Now it's probably the hottest topic in computer graphics, up to the point where I don't really think I can publish much more of it. But there's lots of work on using different approaches and creating environments where individuals can behave as individuals. So there's really two main branches. One is homogeneous environments, which is usually represented mostly by things like evacuation and fire safety. The goal is everybody get out of the building. You don't particularly care about anything but walking. And then the other is heterogeneous populations where people are not particularly worried about getting out of the building. They're doing everything else. And this point of view is to me very interesting because the evacuation scenario is this once in several 100,000 occurrence. If you have to evacuate this building, I hope everyone gets out safely. On the other hand, day in and day out, this building is used by lots of people, and I'm far more interested in what's happening at 99.99999% of the time, where people are actually accomplishing the tasks they're supposed to. There's been surprisingly little work in doing that kind of ongoing behavioral simulation. One of the more interesting ones is actually done, and his name came up in Greg mentioned it, Daniel Tallman and some others in Europe had done a virtual agent Rome. And their agents actually had some interesting actions that were contextually independent. They knew they had to buy bread. If they walked by a store, they looked in the window. And that kind of lent an interesting liveliness to their animations. All right, so the last dozen years or so, we've gone through a lot of graduate students, but also a lot of approaches. And I'm just going to highlight some of these because I have some videos I can show to kind of keep us moving along. One of the students who really got us deeply into this was Nuria Peliciano, and she came over from Valencia, actually. You should look her up, she could probably be a big help. She came over, she's in Barcelona now. And she came on a Fulbright, and she walked in my office. She says, I have a Fulbright for 3 years. I have to get my PhD. Right? Okay, you got 3 years. Let's get to work. And she graduated with a PhD in 3 years and a month. So that's the kind of person she is. And she started working on some aspects of crowd simulation. And the one we started looking at first was something that no other crowd simulation had considered, and that is that people talk to one another. Right? If a fire alarm rings, probably the first thing each of you is going to do, certainly I'm going to ask someone, where do I go? Where's the nearest exit? I see a sign, but is that the right one? Is that the best one? No, I'm going to ask you, are you all going there? Why? Okay, Okay, well, we heard that there's something there, there's communication. The other thing is that a lot of people in this kind of environment don't know where they're going, right? They are in a building that perhaps they're unfamiliar with. I'm certain that probably most of you have not been in this building before. I have not. And yet some of you have. So there's another dimension of interest there, which is some of you know the environment and a lot of us don't. So keep that in mind. We have those two dimensions. We're going to be able to communicate, and we're going to have people who know the environment and who don't. Now, the last variable here was people who were leaders and people who were not. All right. So a leader is basically, you know, this person who just blasts along and thinks they know where they're going, but they might not. Right. So an untrained leader is a leader, but they don't know what they're doing. Right? So now we'll just do some experiments. I'm going to only show parts of these. Hopefully it'll work. So they're not really looking like people. So this one is, no one is trained. No one knows the building, and no one is a leader. So they just wander around in this maze. They form some accidental groups, but those groups explore dead ends. This is the bad one. So they basically just wander. These guys kind of lucked out, right? So this doesn't look like a particularly good situation. Eventually people find their way out, but no, everyone's a follower, so if they got in a group, they tend to stay in a group, but the groups don't know. On the other hand, if everyone is a leader and nobody knows the building, you get a whole different set of behaviors. So if everyone's a leader, so everyone thinks they know what they're doing, but they really don't. So groups don't form, and people, you know, split off groups and they go wander around. Here they're exploring this dead end, happily or unhappily. Yeah, so it's quite chaotic. All right, so when we tried the last experiment, we took 10% trained leaders, that is 10% of the population knew the building and were also leaders. And they were also able to communicate. So if they were in a room, they could communicate their knowledge to other, that's what leaders do, they can communicate their knowledge. And so now, I'm letting this run just a few seconds, what happens is the leaders know the building and everyone else is a follower, so they tend to clump in groups that are well led. So the good news here already is if you're designing a complex building, you need to train about 10% of the people in the building, and they can help everyone else get out. They're almost all out already. Just ran this for a couple of seconds. So if you actually do some experiments with this, you can show that, yep, there's real significant statistical improvements if you let people talk. Not surprisingly, if they can communicate, they're not blind searching anymore. And if you train people, they get out at least twice as fast. All right, so we'll say this crowd stuff is kind of interesting. What else can we do with it? So we thought, all right, well, let's look at the crowd literature, and there was some seminal work that Derek Helbing published a Nature paper, looked at that, and kind of interesting, but not quite what we want to do. And so we built another software platform that let us do some simulation. Crowd noise, right? So we actually were able to start putting human models in there. These are a little hokey. This was a Cal 3D model, but they do kind of walk. Their behavior is totally procedurally driven by the crowd model. And by the time my talk's done, you'll feel like this too. The ones with the red heads are the ones who are hyped up and need coffee. They're pushing through the crowd. So we started looking at some of the psychological characteristics that might affect crowd behavior. So we looked at communication already. So another one we looked at were this social force model, which Helbing had begun looking at, but had some particular issues. And the social force is an interesting model because it says that there's kind of a fifth force in the universe after the physics forces, that there's a social force. And that social force mediates the approach and distance that people take when they're in a group. So I'm just going to show you a little piece of this one. So the basic helping model was formulated with the social forces, but they get these people vibrating a lot because he didn't concern himself with orientation properly. So we essentially fixed the problem of orientation with some other geometric constraints, and we were able to build some really high density crowd movements that are fairly illustrative of what happens in an evacuation scenario. So once again, we're still in this evacuation mode where it happens so rarely, or maybe, I guess that if you work in the real world, these things actually happen a lot in subway stations, railway stations. When a train comes, you get the equivalent of an evacuation scenario. But we kind of stopped looking at that because it was getting to be a crowded field of entertainment. So I had an exchange student from Turkey, Funda Durupinar, and she took an idea that we had and kind of ran with that by giving our agents five-factor personality model. So I'll show you two short clips. The first is there's two kinds of agents. The ones that are colored blue are extroverts, for the most part, and the ones that are white are introverts. Now, what this means in a crowd simulation is this. So they all have the goal of collecting at the coffee table here, and the blue ones are the extroverts, so they all cluster around. The white ones are introverts. So notice, if they're too close to people, they kind of pop out to the periphery, right? So they end up being like the wallflowers. They have to get to their goal, but they don't want to be too close to people. She also explored others I'll show briefly. There's an openness. This is the five-factor ocean model. Openness, so the agents that are red have openness, are very open to new experiences. The ones that have black hair are not open to new experience, and the ones that are blue don't want new experiences at all. And so we put them in a virtual museum with pictures, and the red agents look around and look at all the pictures on the wall. The blue agents say, oh, there's a lot of people here, and this is really not a place I want to be, and the first thing they want to do is escape. So that you can't just build a crowd model. You really have to worry about what the individuals are doing. Oops. All right. So the next part is, well, if personality is important, environment and what people do in the environment must be important as well. So my staff person, who was also a PhD student, Jan Albeck, built a system called Carosa. And Carosa added environmental structure on top of what the pedestrians were doing. So she came up with the name Carosa, which is crowds with aleatoric, reactive, opportunistic, scheduled actions. Almost no one knows what aleatoric means unless you're an electronic musician, but it worked out better in the acronym than random, right? So, and Jan is now doing well at George Mason University. So the idea was now to build this heterogeneous population, not just in terms of personality, but in terms of what they do, right? So the action types Jan explored were scheduled. Okay, we had to be here at 9:15 to start the session. Most of us were here. Reactive, things that are triggered by contextual events or environmental constraints. Walk by the next section, in the next the exhibits, for example. If you're interested in something in one of the exhibits, you'll stop it. Opportunistic are actions that arise from explicit goals and priorities. So, for example, you need coffee and you walk by the snack table and you might pick up a coffee. If you don't want coffee, you might just continue to walk by. And aleatoric are actions chosen from some random set with probabilities that are derived from real life or we make them. So just give you a little video of what Jan did. Now this is done as time lapse because otherwise it would be totally boring. So it's sped up about 10 times normal speed. So there's a lavatory, there's a coffee machine, there's 2 classrooms, there's a lounge, there's some research lab. And everyone's basically going through executing their calendars. They need to do things like use the unisex bathroom, 0. There's classes that are convening, and students are reporting to class and choosing open seats. Eventually, I think this is the teacher. She comes in and comes through the door, and she'll start doing funny gestures that are like lecturing things. Okay, yes, right, so the whole thing is scripted. Actually used Microsoft Outlook as the interface to set all this thing up. And it had some really nice properties. For example, you could rearrange all the rooms and run the same thing. It was not tied to the particular environment. I don't have time to show you all those things, but everything was done with semantic tags, so that we didn't have this limitation of where things were actually placed. All right, well, that's really boring because there's no story. I mean, if you think going to university is a fun story, then I guess it's entertaining. But in the real world, and especially in virtual environments where you want to engage people, you really have to have some reason for them to be in that environment. So I'm trying to resist using the word game, because this is not about games, but really it's about story. Why are you in some virtual environment, and what is it you're expected to do or obtain as part of that experience? So in order to do that, we decided, or we thought, or a graduate student, Alex Schulson, thought that the way to do this was to make the background characters more representative of an active environment. They actually do things. They do things in ways that, let's say, make sense, right? So they interact with the world, they interact with objects, they interact with each other, and they interact with you. So just before Alex started working on this, we had another PhD student and a visitor, and Catherine Stocker and Eva Sun, and they came up with a pretty interesting implementation and idea. The idea is very simple. It's basically that people don't make decisions, events do. Right? So if there's an event like Badler's going to talk, right? Essentially, you all gave up free will, and you were co-opted by that event to come here and sit down and listen. Now, that's not really what happened, but that's what it looks like. And all we care about is what it looks like, right? So humans should do things that suggest intelligence, even if they're not acting in an intelligent way. So this is what a smart event does. And an event says, look, I have to do something, and I need you and you and you and you to come and do something for it. And when that event is over, you're going to be released to go back and do something else or to go out to try another event. Now, what's interesting about this approach is it's extremely lightweight in computation. We don't have some elaborate artificial intelligence cognitive model going on. Our agents basically don't think at all. It's like some poor guy's walking down the street, and the big hook comes, grabs him, and you're going to sit and talk, okay? You didn't know what hit him, but he's going to do what he had to do. So we looked a little bit at some of the psychology involved, and we co-opted, didn't quite use the meaning of the term priming. We co-opted the term priming to indicate the kind of event an agent was likely to participate in. So if an agent was primed for a certain event, they might be more likely to be co-opted for it than an agent that wasn't primed. So in somewhat meaningless theoretical terms, the idea is an event with suitably primed individuals became behaviors that looked appropriate. And also, since events themselves only happened in certain contexts, the context and the constraints of the agents who participated in also ended up with behaviors. So I'm going to just give you a brief idea. I decided to pull the animations because they're laughable. I'd rather show you a little better one. But the main idea is that this priming can occur two ways. One is by location or by interaction. So, for example, we as people have a number of traits. For example, I'm an adult, I'm a teacher, today I'm a speaker, at home, I'm a husband, father, right? We all have those things. But the location I'm in primes those traits. So today I'm a speaker. Okay? Go home, I will not be a speaker, I'll be a husband. And we can also prime by interaction. So if I have a number of traits, depending on the individual that's facing me or the close proximity to, may affect the kind of priming I have and therefore the kind of event I participate in. So for example, a mother may have a daughter, and when they're together it's mother-daughter, but when the daughter's in school, she's a student. So we put these things together with events, and we played with a few kinds of events. One of them was what happens during a fire. So fire is an event. An event happens, and people react. Well, they don't really react. The fire says, you, I'm going to look at what you're trying to do, and you're going to do something, like run away, or you're going to come and try to put me out, right? Or you're going to call the fire department. And all of these things were very easy to construct in simple tables. So we had an interesting game where someone could go around lighting fires and making all the people go crazy, because each fire would be co-opt agents to either put it out or run away or watch it or something. Now, one of the reasons I don't show you those videos is they look kind of hokey and people don't walk right. And for a variety of very strange reasons, they're all dressed as 16th century Indians. Since we happen to have those human models handy. So a most important thing happened a couple of years ago is we switched all of our graphics to a game engine called Unity 3D. This is just a glimpse of what the interface looks like. All of our students who do anything interactive now learn Unity 3D, and they basically learn it overnight. It's very easy. So it's got a variety of interfaces. It's nice in real time because it's a game engine. It's got all the features you want, and it's very easy to construct things. So one of the first things we did is, well, let's choose some event that has sort of this not escape and not panic situation, no fire, no evacuation, no disaster. And we said, well, what kind of things do people do together a lot? Conversation. So we thought about conversation, and we came up with 14 different conversation types. There are probably more, but these are two things that two people can do when they communicate. And what I mean by do, I mean the sort of geometric configuration between them. They can both stand facing each other, they can be seated on a park bench, they can be walking, passing each other, one can be using a cell phone, you can see the other one, so forth. So what's going on in an environment? We said, well, given an environment, events, these conversation events, would happen with some distribution, right? So, for example, the kinds of conversations that happen on the street are probably more walking together or crossing kinds of conversations, whereas what happens in a restaurant is probably more seated interactions, right? But where did we come up with these numbers? We totally made them up. Not a single survey was made other than sitting in Cooksie and taking some handouts, okay? These were totally made up. But you can see in different environments, there are different kinds of conversational types that predominate, but others can occur. We also looked at the kinds of conversations that were going on, and we came up with 4. There are probably many more, and it might be that in more kinds of environments, there may be some very interesting cases we didn't look at. But we had 4 archetypes: simple question answering. Okay, where's the restaurant? Right? When is it going to be snack time? Friendly chatting, you know, chat. Okay. Bargaining. I need to buy this. How much is it? It's too much. Can I give you some less? Some negotiation. Or arguing. So we said, well, again, how frequently do these kinds of archetypes occur in different environments? And for example, on the street, you might get mostly friendly chatting and an occasional argument. But if you're in a restaurant, you're probably not going to be doing too much bargaining if you want to have food and so forth. All right, so we made up all the numbers, and then we just let things run. So here's a marketplace, and these guys are wandering around, and they have only this conversational behavior and a shopping list. So they may have a conversation, like those 2 guys in the center, but they may pass and not have a conversation. They have a shopping list, so they need to visit some of the stalls, and they may negotiate for food, or they may give up, or they may argue. It's just a simple behavior that drives the entire animation. All right, so we're going to see the marketplace a little bit more, but that's a very simple underlying statistical model. If I had real data, I could have more real distributions, but this one works well. So how do we represent what's going on? So up until a few years ago, we were working with a system that we built called parameterized action representation, and it was a little crusty and awkward, and it didn't have good syntax, and no real formal basis. And Alex Schulson put us on a much more stable formal framework by forcing us into what are called behavior trees, or really just and/or trees. So the primitives here from a programmatic point of view are very simple. You either do things in order, that's a sequence, you do things with some priority, or alternatives. If you do the first one, you don't have to do the second and third, for example. You have a stochastic selector, so do one of those three things with some given priority, given probability. Or you can have a subtree that you execute. So this is basically almost all that programming languages do. So it has the power of a programming language, but it forces you into a very nice graphical structure. So here's a conversation behavior tree running. This is what the tree looks like. So this is conversation with two actors, A1 and A2, and they're going to meet somewhere at some position. And what they're going to do is they're going to get to the meeting points. They're going to look at each other, and then they're going to enter this loop where they're going to randomly choose gestures and gesticulate. So the agents have no thoughts. The agents are going to be totally controlled. Right? Let's run this. So you're here. All right. They don't want to come out hiding. All right. And why? Well, we'll see some others in the room. That's surprising. All right, so what ADAPT does is it combines three key notions of what people do in the environment: the behavior, how they navigate, and what they actually do. So the behavior, we use these parameterized behavior trees. So you could think of them loosely as a scripting mechanism, but they really right now are program chunks in this formal language. The nav mesh and steering just gets people around the environment so they don't bump into walls and each other. And the animation coordinator controls the bodies. So earlier, as mentioned, Jack, we don't use Jack anymore, we use another body, but we control it through what we call choreographers. It may not be a great name, but the choreographers control different parts of the body, and then they're blended together to actually give final animation result. And of course, we just duplicate this for multiple characters. All right, so this one. Why the animations don't work right here? It's interesting. Oh, because we changed the resolution. Nice. This is very interesting. Can you tell me what you changed it to? You didn't change it? I'm trying to blame you. I'm sorry. All right. No, it's my fault. Subway trip. All right. So I'll tell you what's going on. The idea is that there is a shadow body that is being controlled by the locomotion choreographer. A shadow body is being controlled by the reach. A shadow body that's being controlled by the gaze, and a shadow that's being controlled by physics. And each of these controllers moves the body, and then we blend together the results of all those controllers. So you can see here, unfortunately not animated, I don't understand why, that the upper body gesture controller wants to put the body this way, but the locomotion controller wants to put it in another position, and they have to agree to put your arm in one place. So there's a nice blending mechanism that makes sure these things hang together properly. Another thing that can be used is an actual Connect interface. It doesn't have to be Connect, it can be motion capture system. So this is real time, and you can control the character with your body as it plays. So this is going to play either. Well, maybe if we unplug the video later on, I don't know why this isn't playing, I can show you that. All right, my apologies. Worked before I got here, that's a bad excuse. All right, so what are we doing the last year or so? We actually have money, our only current grant in my lab is part of a very large consortium called the Robotics Collaborative Technology Alliance from the Army. And indeed, I am not interested in robots, I apologize, Greg. But the interest in robots is how do they coordinate and collaborate with humans? And in particular, how can people communicate effectively to robots to get them to be part of a team? The two things that we do in this are, one is the multimodal interface part, and I'll give you an example of that in a moment. And the second is, perhaps understandably, building a virtual environment in which the human and robot teams can actually work and do their jobs. And Marketplace is just an example of that. So, so over here on the right corner is the representation of a smartphone with a screen. The screen can be used to show what the robot camera takes pictures of. But the smartphone itself is actually used as a gesture controller to guide the guy in the center, who's the team leader. So basically, you're like moving the thumb like this to say forward, stop, left, right. So gestural interface. And of course, we have the populace here who react in different ways to the presence of the soldier and the robot. These guys appear to be upset. This guy seems to be not too concerned, although he's more interested as bananas don't get taken. And other people have these conversational behaviors and react in various ways. So we can put all these pieces together in an environment which has sort of visual richness and an interactive richness, and actually give those characters behaviors that make sense both with respect to each other and with respect to these interlopers who've come into their environment. Since I have a few more moments, I'll show you something that's a little bit on the side. I mentioned the word artificial intelligence, but I haven't yet used the word planning. And this is because I think that from the AI perspective, often people think of planning as a solution to everything. I was very fortunate to have for almost 2 years a postdoc, Basha Kapadia, who's just taken a position in Disney Research in Zurich. And he was really good at planning. And so we adapted some of his ideas in many of these demos, but in some of the work that we did. And I'll just show you some video. I'll talk over it. I'm not sure we see the whole thing if it runs. It doesn't run. Okay. Look at all the embedded videos here. So that's not going to show. Anyway, so the point of this one is kind of an unusual situation where there are dynamic obstacles. Everyone has a goal. It doesn't necessarily have to be to get out. They all have a goal to, say, meet at some place at the same time. They all have obstacles to confront. They have other agents, other people to avoid. And some of the obstacles are dynamic, so this rolls back and forth, and they have to jump over. Too bad. All right, so what are some of the research directions that we're currently pursuing? So the ADAPT platform with the choreographers that control the bodies and the animations and the marketplace, for example, is presently being expanded with some machine learning to understand how people interact with objects in the environment. We are actually using machine learning in another related project that I don't have video to show you of learning how people respond to different crowd situations with respect to steering. So if there's a big knot of people, it's unlikely I'm going to try to walk right through you and walk that's one way of incorporating actual human behaviors into steering virtual people. There's an important question which actually makes sense in this community is, I've got all these tools and yet I'm probably building things that are not realistic. What do real people do in an environment? What do real people do when they're out in the marketplace? The Army wants us, not surprisingly, to build culture-specific populations. We used a generic Middle Eastern village and marketplace that my Middle Eastern friends tell me is not right, but it's expensive to build the pieces to make that work, although that's something we will eventually. But getting the cultural responses is relatively easy because we can go into the agents and we can change the kinds of behavior trees and the numbers in the behavior trees for making gesture choices and so forth. We know how to do them, we don't know what the numbers are. But any time you build an environment and you want to transplant it into the different communities you all represent, you're going to want to do that in some relatively easy way. You don't want to build 70 different simulations for 70 different cultures. You don't want to build it from scratch. So that parameters to tweak. The other part that we'll try, since this seems to, well, this one works, is we come back to this issue of communication between agents. And we spent a lot of time the last few years building an audio sense into our agents. Now, what this means, and I'll show you in a moment, but imagine you have this marketplace full of people and someone, let's say, sets off a firecracker, okay? It's loud bang. You would like people who can see it to still react to it because they hear it. And for people who are further away, maybe they don't even hear it and they don't care. Or maybe some people react to that loud sound by some behavior. They might run away or come and see, run over and see what it does. So we've been building sound propagation with all the rights to physical properties into this virtual environment and giving the agents a sound perception sense so they can interpret, if they hear anything, what they might have heard. So let's turn this
Simulations only consider visual perception while modeling agent behavior.
Maybe that's what
In this paper, we present an agent-based sound propagation and perception framework, enabling characters to hear, classify, and react to virtual sounds in the environment. The red agent draws the attention of the green agent by whistling from an appropriate vantage point.
All right, so that went by really quick.
Sounds are hierarchically clustered and categorized based on a heap.
That's probably where they went. All right, so what was going on there is, sorry, creating chaos. All right, so what was going on there is the sounds that were created were propagated through the environment, and each agent has a hierarchical decision tree. And when it hears sound packets, it tries to categorize them. And if it gets a unique hit, it says, oh, I heard the whistle, or I heard the gun, I heard the blast break. But if it's a little fuzzy because it's degraded, it goes higher up in the hierarchy. You might say, I heard something, I don't know what it is, so I'm not going to react to it. And this is not just by distance, it's affected by the presence of other obstacles and other agents, so the environment actually has different sound propagation properties as things happen in the environment. This has been a very interesting addition, and it gives a nice feature that when you have an environment and you want to refer to people, we can actually call out by name. So if we say John, and if John hears the phonemes in his name because he's close enough and they haven't been distorted, you can actually get John to do something. But if John is behind a wall, or he's behind a building, or he's where there's a lot of echoes, he might not have heard his name clearly, he's going to ignore you. So it leads to a much more human level interaction with animated agents because they have basically some capacity to hear. Finally, we're interested in working towards getting a story engine to drive all this. Nothing I showed you was really interesting from a story perspective, but we've now incorporated a planner with a story generator where these planner generates events for people along some narrative arc. And that is hopefully going to show in a year or so that we can generate immersive stories that are widely variable without having to build individually each particular one. All right, so except for my videos, which I think we're all playing in the background, I'm going to actually just go back and try at least if I can do this one. Since that may have been what happened. I can't do it. Nah, it didn't come up. I have to admit to being mystified. All right. So, let me reiterate, besides trying to do the Truman Show, which we're not quite there yet, the goal is to construct real-time. Everything I showed you at the end was all real-time animation done in the game engine. So real-time is here. Virtual environments, they're all 3D, they're all populated, humans, characters, robots. The individuals had meaningful goals. They can be co-opted by events. They had conversations. They can react to the soldier. They're heterogeneous. They're all different if you want them to be. They can be communication aware. They have a sense of hearing, and they also have a sense of vision. I mean, they know who they can see, but now they also know who they can hear. And they interact with each other and with the participant. So, if nothing else, I hope that even if my videos didn't work, that this is going to give you a possible vision for new applications that you might have for virtual environments. I don't want to use the word rehabilitation quite because I don't know how to make that connection to what you each individually do, but perhaps that connection will come from what I've told you. Thank you so much for your attention, and I'll be happy to take a couple of questions, except my video didn't work. Thanks.
Norm, it's been crossing my mind as you were speaking, and you did mention briefly about the different cultural experiences, and what came to my mind was, having grown up in New York, people don't line up when they're in a crowd and they're trying to get somewhere, they're clustered. And I go to England and everybody's in this nice polite line and they look at their turns. So there is a lot of cultural difference, but I'm wondering how you predict it or how you decide which of these are you going to build in?
That's a good question. So the question is, how do you build essentially personality and cultural variables? And the answer is you build them as parameters. Okay? You don't just build the New York simulator. The way to view it is if you recall the ones that do work, the ocean character, OCEA personality types. Those are like 4 dials. You can simply change the numbers in those 4 dimensions, and you get different behaviors in the category, in the characters. So the job we have, and by we I mean the computer animation, computer science folks, is what is the mapping from the parameter set to behaviors. And it's not easy to elucidate those mappings. We do a lot of, well, I think it should be this. But we actually have one experiment that's in progress now that's being redesigned to be better, which is to connect the ocean personality types with the specific way gestures are executed. So we're coming back to old topics that I looked at a long time ago, a lot of movement analysis, and trying to elucidate if there's any connection between personality and the kinds of movements that people execute. And again, if we can parameterize them, then if you have a personality type and you dial it, your gestures will be different, not just the way you do it. So That's the other holy grail is give me a set of parameters and I build a procedural model that allows you to teach.
Does anyone else have a question before I ask my next one? Right.
I was thinking that gestures are also cultural. You know what you have as an introvert in Europe, let's say, it's probably some issues that an introvert has. And gestures are also pretty magnetic. Something like this, that's sort of
Right, we actually used, that's a very good point, that gesture performance and choice is culturally dependent. And we have access to a database that was put together at the University of Central Florida of 1,000 gestures across cultures. And exactly those things arise. The problem with that database is there are no animations. So it simply says, yeah, it's a nod with an arrow that goes up and down. And it's very difficult to elucidate, even within one culture, what these things, what kind of movement. Very fine, subtle difference.
All right, so the second question is actually relates more to parents. So we all know the work done, for example, at USC, where they have a virtual patient who responds to a trainee or psychologist, for example. And have you thought maybe using your crowd simulation integrated with that? So what they done at USC is single person, right? A single patient. Right? But there's also crowd, schizophrenia and so on, craziness of the crowd. And crowd we actually have ecology depending on what's happening, on traumatic situations, for example. All right?
Sorry, after I ask my question, I'm going to repeat it briefly. So Norm he's well known for his crowd simulation, among other things, and we all know about work done at several universities in the US, probably outside too, on virtual patients that are used as dummies, electronic dummies to train novice physicians or psychologists. And I was wondering whether you can, in fact, extrapolate that one level of magnitude and apply it to crowd, especially in catastrophic situations, and see whether something like that can be used. Because we always, after, let's say, mass shooting, for example, the psychologist has to go there and counsel, right? So I'm just saying, if you can.
I'm not sure I know how to best answer the question. I'm going to toss it back a little bit by saying, if you have some kind of therapeutic regime where you can present a variety of people to your subject, then anything that allows you to parameterize and vary the kinds of stimulus you give a person may be of therapeutic value. Whether those virtual people should be presented one at a time or as a group may in itself be interesting. I think
for example, in family counseling, where you have one psychologist and the father, the mother, the young teenager who backs up. So then you're dealing with three people, not one which has been already done.
Right. So I think the way I would view the desirability of having a group of people as a group session is, and if I'm beyond my edge here, I apologize. The therapist may be looking for anomalous behaviors, even of people who aren't talking. So in a group situation, for example, I think I know better situations of surveillance. Let's leave the therapy aside. If you have a group of people and you're watching that people for anomalous behaviors, then you have to filter out all the things that are normally done in that so that you focus on the one that looks anomalous. So for example, the person who seems to be wandering around and starting and stopping and not really having a focused goal is probably a lot more interesting to focus on than someone who's just walking in a very deliberate fashion from place A to B. A person who's looking around a lot is going to look like they're suspicious. Now, whether those have kinds of therapeutic analogs, it's not for me to say, but if you can create them in some virtual environment where you can explore either the training of the therapist herself or the therapy of a like person, I think this has some relation to that. And we don't do it, so these are openings for partnerships perhaps as well. We would welcome further exploration.
Do you want to ask?
Can I just do one more quick one, and then we should end? I just wondered, Norm, if you consider that behaviors you're modeling here also apply to driving simulations, driving in crowded traffic, because I often think it's kind of like a dance between the cars, and the same line of behavior that I think you see in human interaction you see when they're driving.
Emily, that's a great question. I'll answer it quickly. One is, I'm glad cars don't behave like people do, right? Because collisions between people are allowed. Secondly, I think when we looked at driving, as we did for a while, we became very interested in human gaze behaviors. It's all about perception, and most of that is visual. And we actually, with a former PhD student, did some work on human visual attention. And we were able, with a very simple, non-validated model, to get somewhat realistic behaviors purely from the inability of a person to focus on too many events at once, right? So while driving, if there are too many things happening, you won't see the ball roll in the street and the kid, right? But if there's nothing else happening, then your attention can be focused on any anomalous event. So busy environments are dangerous ones. I think from a driving perspective, the best thing that can happen when attention gets taxed is just slow down. So we did that work, but we decided that driving was a really hard special problem that was heavily dependent on attention models. And I think at that point we bailed out of our level of confidence. Thank you. Thank you again for your attention. It's been a pleasure to be here.
Thank you.
And ask you if you don't mind hanging around with the break here to maybe show the videos who'd like to come on.
I'm sorry. Quick announcements. First, I want to inform Norm that we've been videotaping you, and I hope you don't mind if we upload your talk on our website. Okay, so you all know if you want to go back and hear some more, it will be there. The presentations for the session coming up, not all of them have been uploaded. Please go over to Joe. Joe, raise your hand, please. If you haven't had your presentation uploaded, or if you're planning to use your own computer, just let him know so he can help you out. Posters that have not yet been